We're going to talk about the three major types of electronic temperature sensors that are being used in industry. Back in 1800, Andres Alessandro Volta, an Italian physicist, invented the electric battery, and that opened the door for a lot of experimentation with electrical devices. And in his honor, the unit of electromotive force, volt, was named after him. The first two temperature sensors were thermocouples and RTDs. The first one was a thermocouple consisting of two dissimilar metals joined together to form a circuit. In 1821, T.J. Seebeck discovered that a current could be produced by unequally heating two junctions, what's called the hot junction and the cold junction of two dissimilar metals, the thermocouple effect. Seebeck assigned constants to each type of metal and used these constants to compute the total amount of current flowing. The EMF, or electromotive force, that produced the current is referred to as the thermocouple EMF, thermoelectric effect, or as the Seebeck voltage. In 1821, Humphrey Davy discovered that all metals all have a positive temperature coefficient of resistance. In 1871, Werner von Siemens invented the platinum resistance temperature detector. Initially, it fell out of favor due to temperature readings becoming unstable, and Hugh Longburn Callender discovered that the insulator that Siemens was using was causing the platinum to become brittle, which caused internal stresses, and that produced a temperature instability. He changed the insulator material, annealed the RTD at temperatures above the highest desired measurement temperature, and developed the first commercially successful platinum RTD in 1885. These two discoveries, thermocouples and RTDs, marked the beginning of serious electrical sensors. The 20th century saw the discovery of semiconductor devices such as a thermistor, integrated circuit sensor, a range of non-contact sensors, and fiber optic temperature sensors. So what we're going to talk about today are the common types of sensors used in industry. Non-resistant sensors, which are thermocouples, resistance sensors, which are RTDs, semiconductors, which include thermistors, positive temperature and negative temperature coefficient versions, and diodes. And there's also infrared, which we won't get into today. Thermocouples most commonly are base metal alloys that are used in severe and demanding environments. The choice of a specific style is to a large degree determined by the temperature working range, ambient atmosphere, or media conditions such as the size and shape required for the application. Control requirements such as accuracy and speed of response may also be considerations. Two wires of any dissimilar metal can be connected to each other at one end, the hot junction, and the other ends to a reference junction, which is called the cold junction. Certain metal pairs have good, quite linear behavior and temperature change and good temperature gradients, so they are put together as types of thermocouples. So we have the heated junction. This particular picture is of a type J thermocouple. You see one of the wires is iron, the other is copper. When you heat one end and the other end's a different temperature, it will generate a small voltage signal. And this is predicted by the different types of resistance each wire has, according to the IEC 1977 specs. All thermocouples, regardless of where they're manufactured anywhere around the world, are manufactured the same specs, so they're all interchangeable. A thermocouple needs a cold junction compensation to work. The classical thermocouple configuration, the original ones, used an ice bath, water bath, to set as a reference temperature, as shown in this figure 1. Points 1 and 2 are kept at the same temperature by using an isothermal block, which is an insulator used to make sure that both points are at the same temperature. The cold junction temperature is here using this ice bath, and it's referenced to a temperature of 0 degrees C. Another diagram, you have your hot junction, there's a candle under the sensor. You have your terminal blocks. This terminal block is an isothermal block designed to keep both of the two junctions from the other end of the wire at the same temperature of each other. And then you have a voltmeter which measures the voltage. None of these electronic sensors are actually measuring temperature. They're all measuring voltage. So if we take this classical thermocouple configuration using an ice water as a reference temperature, that's not practical in the real world because you can't carry that around with you. It's fine for a lab. So we have to have some kind of a other reference signal. So you have your two wires that are hooked together at your hot junction. That's what's heated or cooled. The other two are put on this isothermal block. And then there's something on the isothermal block. It could be a thermistor, an RTD sensor, or a diode that's measuring the ambient temperature around it. And that ambient temperature is referenced to 0°C. So this cold junction is required to make this thing work. The thermometer is referenced to 0°C. If I have at the hot junction, if I have 900 degrees Fahrenheit, and if I have 0 at the cold junction, I'll get the same signal as if I have 100 degrees and 0, or if I have 900 degrees and 800 degrees. It's the differential causing this signal. So I have to have a reference to tell me where I am. So we have a, say it's 75 degrees ambient. The 75 degrees ambient is measured from 0 Celsius, which is 32 Fahrenheit, or 75°C in this picture. But anyway, that temperature difference is a voltage calculated to give you a temperature, and then the cold junction temperature minus 0°C is added back to it, and that's the temperature is displayed on the meter that you are looking at. So we have a measuring instrument here that amplifies this millivolt signal. The signal is very weak, so it needs to be amplified to be read by a meter. So I have a cold junction and a hot junction going to the meter. There's a thermistor on the cold junction measuring the temperature, and that gives me my ambient temperature, which is added back, or reference to 0°C, and the difference is added back to the signal coming from the hot ends of the thermocouple, and it's that's your temperature you're seeing. So thermocouples are subject to possible external noise issues due to the small magnitude of the Seebeck voltage. In harsh environments with a lot of electrical noise around, appropriate filters must be applied along with shielded wires. The thicker the thermocouple junction, where the two wires are connected, the higher temperatures it can measure, but it will also have a slower speed of response. When measured in conductive mediums like water, the thermocouple sensor must be isolated. You can't use a bare junction thermocouple in a conductive liquid. The section of the optimal thermocouple type wire metals is based on application temperature, atmosphere, required length of service, accuracy, and cost. When replacement is required, it is important that the thermocouple type matches the old one, or the measuring instrument reading that thermocouple has to be reconfigured to a different type. Different thermocouple types have very different voltage output curves. To prevent large errors, it's necessary to use the proper type of thermocouple or extension wire all the way from the sensing element to the measuring instrument. If the cables of the thermocouple wires must be extended to reach a controller, it's best to use thermocouple extension wires of the same type. If you use a Type K thermocouples as a sensor, you should use Type K thermocouple wire for your extension. If that's not possible, you can use copper wire to go from a thermocouple to your controller, but the whole length of that copper wire has to be the same temperature as your cold junction, so it can be performed at the controller instead of at where the copper wires and the thermocouple wires are attached. Three basic types of thermocouples here. We have an exposed tip, we have ungrounded and grounded construction. The junction of exposed tip, which is a bare wire thermocouple, is exposed to the surrounding environment. That's fine for air, some powders, things like that, but it cannot be put into a conductive liquid. Ungrounded or insulated junctions are electrically and physically isolated from the sheath material. Those are good for control loops where you're not grounding your control loop out. They're a little bit slower in response, but they will work for control loops. Grounded thermocouples actually have the two wires will be welded to the inside of the metal sheath, and the metal sheath will complete the junction. So here we have a common type of a grounded thermocouple, mostly used for handheld things and people who want fast response but are not using control loops. The speed of response is generally at least 50% better than an ungrounded one. In these cases, the two wires are grounded individually to the inside of the metal sheath, and the tip of the probe completes the circuit. As long as that tip is the same temperature as both sides of this thermocouple junction, it's the same as them being connected together. Most common type for controls is a isolated or ungrounded one where the thermocouple element itself does not touch the metal sheath. It's electrically and physically isolated. It's a little bit slower, but it's you can't have it grounding out your control loop. Also, they will last longer because they're subject to less direct vibration, which could break the welds where they're welded to the inside of the sheath, and the powder around them will protect them from vibration. And there's some lower level of accuracy for very small diameter probes and short probe lengths because of heat transfer up the probe. The third and least common type is the exposed type. This is where the wires actually protrude out the end of the sheath and they're exposed to the surrounding environment. These are very good for limited applications, dry, non-corrosive, non-pressurized applications. They're much faster than the others, which are enclosed in a sheath. They are subject to corrosion and physical damage if they're used in the wrong environment, so that needs to be kept in consideration. The two types are twisted and then welded, or the two wires are butt welded together. We use them in a number of air probes on handheld instruments because they're much faster in response. Extension wires are usually higher grade material made of the same metals as what's called special limits of error thermocouples. That's to transmit your data from your voltage from the probe out to a controller or a recorder. If you have to run some distance away, you would not want to use a different material which would generate an unwanted voltage where the junctions is connected. The sensor wires, being of light metals, do not generate an additional voltage, so they're good for that. For platinum thermocouples, which are usually used for very high temperatures, extension wire is usually a copper alloy since it's extremely expensive to use platinum wire for these extension wires. The extension wire is specified to have a very similar EMF thermal coefficient to the thermocouple, but is only suitable over a narrow range of temperatures. But this will significantly lower the cost of this application. The temperature measuring instrument must have a high input impedance to prevent any significant current draw from the thermocouple to prevent a resistive voltage drop across the wire. You don't want the instrument pulling from your thermocouple voltage. You don't want it just reading it. Different thermocouples have different curves, but they're all basically an S-shaped curve to one extent or another, so they're not linear. You need to have a microprocessor to linearize them for best accuracy to straighten out that curve so you'll get the same accuracy up and down the scale. Here's a couple of different thermocouples. The one on the left is just a standard one. You have your hot junction where the two wires come together, your cold junction on the isothermal board. Then on the right we have an averaging thermocouple where you have a series of thermocouples maybe up and down the length of a probe, all going back to a common cold junction. What that does is average the reading all along those different thermocouples. So if you're doing like you have a 3 or 4 foot immersion, you want to average it all the way across that immersion depth, this is the way to go. So you have 2 or more thermocouples going to a common cold junction. A thermopile is a series of thermocouples that are put together, each tied one to another in series, and this is generating a average voltage across that tip. The most common thermopile thermocouple that people will see is an infrared thermometer. The sensor is a cluster of thermocouples in a thermopile. The energy is received and concentrated by a parabolic mirror onto this cluster of thermocouples, and that's how you get your temperature on an infrared thermometer. More of these same things, differential temperatures, where you have thermocouples connected in series, and you have your copper wires going from one end to the other. That's where your cold junction is, where the copper wires are connected to the thermocouples, and it's important that the copper wires, the red wires going back to the reference thermometer, are all kept at the same temperature along those wires. And more pictures of averaging thermocouples. It's the wiring diagram. So a differential thermocouple is where you have two wires of the same material for your outer wires, then you have a different material that's connecting the two of them, and you have to have a special instrument that will read the differential. So this gives a differential temperature between the two hot junctions. Purpose of connection heads for thermocouple and RTD probes is a place for the probe to screw into. The wires come out into a protected area. They're connected to a terminal block, either with a transmitter output from there or another connection for extension wire to run out to your end use. The connection heads are available for a lot of different applications. We have conduit connectors where you can run your wire back through conduits and protect them. We have cast aluminum, cast iron with aluminum covers or cast iron covers. These are weatherproof areas. We have stainless steel heads and covers for food and dairy or weatherproof requirements. Polypropylene for extremely corrosive areas or also other food and dairy applications. And then heavy iron or aluminum housings for explosion-proof applications. Extension wire, we can supply that on rolls if you need that to go with a particular probe. So advantages: it's self-generating signal off of a thermocouple. It needs no external power source to power the probe. They're low cost, relatively good accuracy, fairly good stability, good resolution, generally very fast. Speed of response is always a function of the probe mass. Thermocouples have the least response or least mass of any of the sensors, so they're the fastest. Very wide temperature ranges. Some of the common ones would go down. You can take a thermocouple down to minus 200 Fahrenheit, although very few people go down there because the signal is so weak at those very cold temperatures, you really have to amplify it greatly to read it, all the way up to 2600 C. Thermocouple can be grounded and brought into direct contact with the material being measured, so it's very fast and also very rugged construction. Disadvantage: you have requires two junctions, two temperatures to be measured, at the hot junction and at the cold junction. The signal is very weak in a thermocouple, so it's very subject to being interfered with by any outside electrical voltages, so it's required to be properly shielded. Never run thermocouple wire without proper shielding next to a big electric motor or something like that. The measurement is taken across from the sensor across the length of the thermocouple wire, over how long the probe is, and the wiring it's transmitting. So if you have corrosion along that, it will affect the signal. So homogeneity will be affected, especially if you use a thermocouple like a type J, where one of the wires is iron. You'll have a lot of rust problems, corrosion problems along that. So make sure that those are protected from the elements if possible. Different accuracies will vary. There's standard limits of error wire and special limits of error wire, plus meter specs. We'll get into that in a little bit more in a few minutes. They're fairly stable. They drift over time. There's an entire industry out there of what's called thermocouple recalibration equipment. Once a thermocouple probe is made, you cannot recalibrate it. What you're doing is, as it drifts, you're building an offset into the meter for the error. So you constantly have to read the error and then make allowances for it in the meter on thermocouples. Good resolution, higher temperatures, very bad resolution, or very unresponsive to very low temperatures where the signal's weak. Nonlinear curves, ideally you should have a microprocessor to straighten them out for best accuracy. If accuracy and stability are required, the calibration of the installed sensors must be checked frequently, especially if you're getting a lot of temperature cycles and you're running up to high temperatures. That will make them change much more rapidly. Also, because there can be corrosion along the length of the probe, either the wire inside the probe or the transmission wire, they ideally should be checked in place. If you pull them out and hook them up to a different set of wires, you won't have exactly the same situation. And long lead wire thermocouples can be expensive, as thermocouple wires will add up in cost. So for a lot of people, a transmitter is the best application there, where you're sending 4 to 20 over copper wire long distances rather than filling with thermocouple wire. Potential decalibration, process of unintentionally altering the makeup of the thermocouple. This can be caused by diffusion of atmospheric particles into the metal at the extremes of the operating temperature range. Any thermocouple that operates above 2,000 degrees needs to have the sensor shielded inside of glass or quartz, because the oxygen will corrode it terribly and it won't last very long. It's always good to use insulated junctions where possible when you're making thermocouple connections, protect them against oxidation and contamination. These are 3 commonly used thermocouples: Type J, Type K, and Type T. Type K is the most common. For those looking for extreme accuracy, you can see that the accuracy is not great on either one. Special limits of error wire has pretty much twice as good accuracy as standard limits of error. The difference in them is the alloys made to use the wire are purer. They're more highly refined alloys, so that's the reason for the better accuracy. Just costs more, but they are a much better accuracy unit. But again, for precision work, you will see the wires themselves have errors, probably will put you outside of the realm of what you need. So you would, if you use them, you have to build an offset into the meter to take care of it. These are the other types of thermocouples. We have the exotic, the noble metal thermocouples with platinum in them. And these are very expensive probes, very high temperature. They generally won't work very well down low because of the voltage is required. And here a Type B gives the same output as 0C and 42C, so they're worthless below 50C. So these are specialized applications. A lot of people are starting to replace Type Ks with Type Ns. It's a little more expensive, but it's more stable and offers improved accuracy. Now we're going to go from thermocouples to resistance elements. RTDs, resistance temperature detectors, are devices. People use either term. There are wire wound and thin film sensors out there. PT100 is the most common. That's a 100 ohm platinum sensor, but there are others available. Then we have semiconductors, thermistors. We only build thermistors in handheld instruments. We have done some work on some specialized fixed instruments, but it's not in our standard product line. We have positive temperature coefficient, PTC. We don't use that, and it's not very well or largely used in the industry anymore. Negative temperature coefficient, NTC, that's the most common ones out there. Diodes, we don't use any of them here. In a resistance element thermometer, power is sent from an external device or a meter through the resistance element and returned to the meter. In simplistic terms, we're measuring the difference on what we send out and what we get back. This is true for thermistors, other semiconductor sensors, and 2-wire RTDs. And we'll discuss other RTD configurations later. So you have a sensor with a known temperature coefficient. The resistance change correlates with the temperature which is displayed or sent to a recorder or controller. A thermistor is a semiconductor which changes resistance with temperature, a very high rate of resistance change generally. This is manufactured from oxides of transition metals, manganese, cobalt, copper, and nickel, powdered metals fused into a chip. It's the most commonly used electronic temperature sensor out there now. all of your fever thermometers, your air conditioning controls, thermostats, things like that use thermistor sensors. They're very, very small, typically 2 to 3 millimeters, a round blob, 2 wires coming out. They're coated with glass or epoxy. Since the powder, the chips made from this powder is very highly hydroscopic, will absorb water like crazy. 2 types, PTC and TC. They typically operate at 5 or 10,000 ohms of resistance at these 2 standardized temperatures. However, many people use their own curves, so there's not really very many standardized curves in the industry for thermistors. Positive temperature coefficient. As the temperature went up, the resistance went up. Since they operate at very high resistance levels, they tended to get very hot. So you had to deal with the self-heating problems caused by that higher level of resistance. NTC's negative temperature coefficient, temperature goes up, the resistance goes down, so you don't have to deal with the self-heating issues. Typically, thermistors are good. Most common thermistors are good up to about 500 Fahrenheit. There are some specialty units out there made by Yellow Springs that you can go up to 1000 C. They're made with exotic metals. They're quite expensive, specialized use. Thermistors are nonlinear and require some sort of microprocessor to linearize them to make sense of the reading. So the advantages: resistance type sensor, more accurate, lower cost, wider temperature ranges are more costly. High accuracy can be obtained with high quality versions. Good stability, much better than thermocouples, but the stability does increase with age as they settle in. High temperature coefficient for greater resolution. You get a very large resistance change with a minute temperature change, so it will show small changes. Pretty fast response, small probe mass. High resistance makes lead wire resistance a minor issue, so you don't have to worry about that issue. We talked about positive temperature coefficient, negative temperature coefficient. High cost for sensors if you have a very wide temperature range. They're generally used for low temperature applications. They can be affected by electromagnetic interference if not properly shielded. Long stability is good, not as good as RTDs, much better than thermocouples. Not suitable for large temperature spans. We don't use PTCs because of self-heating issues. Non-linear requires a microprocessor. Most thermistor sensors use a table lookup system where they'll have a little guy in a thermometer reading his book. He gets a resistance reading, he looks in his book to see what the temperature is, displays that. So it's got to have a lot of memory if you're using a thermistor. Short temperature range except for specialized exotic metal versions. Poor interchangeability. Since there's not a lot of standardized curves, you can't interchange with other instrumentation very easily. RTDs are based on the fact that resistance of temperature or metal wire increases with temperature. Practical devices are made of metals that exhibit relatively large temperature coefficients of resistance. When RTDs first appeared, the only practical way to make them was to wind a fine metal wire around a non-conducting mandrel. The best choice for RTDs has been platinum because it has a very high resistivity, it's very stable, and does not alloy into another metal regardless of what conditions it's exposed to. This non-conductive mandrel is usually a ceramic or a glass mandrel, so that makes them fragile. Platinum is expensive, and the ability to make fine wire from it was not nearly as easy as it is today. Because of this, RTDs have been made from assorted metals, the most popular of which were copper, nickel, and iron nickel, which was called Balco alloy, which was used in the power industry many years ago. Although all these metals have positive temperature coefficients, each has a different characteristic. Their temperature coefficients of resistance differ in magnitude and linearity, and each have a different resistivity. Copper is the most linear with the lowest resistivity. It was used by many electrical power generators and transformer manufacturers. Its low resistivity led to the 10 ohm copper RTD, which was commonly used many years ago, not used too much anymore. Nickel iron alloys were used because they have higher temperature coefficients, and the wire is both easier to work with and less costly than platinum. The nickel iron alloy increased in popularity because it was made specially for temperature sensor use, and its high resistivity has supported higher resistance RTD elements. The properties of pure nickel has changed through times as the ability to produce higher purity grades improved. While nickel and the nickel alloy are relatively stable, they do not rival platinum. The materials are not interchangeable from batch to batch, and operation is limited to no higher than 260 degrees C. The added processing required to attain reasonable interchangeability adds more cost than can be saved by substituting them for platinum. The use of nickel in new sensor design continues because it may be formed by chemically etching into various useful configurations. In the end, platinum is much more stable, and no other material can even come close when it comes to long-term temperature measurement. The ability to purify platinum and the understanding of its characteristics led to the early development of very stable but also very expensive sensors. Currently, the lower cost of manufacturing platinum wire eliminates any justification to use other metals. In most cases, platinum now costs less than it used to because of better ways of manufacturing. The ongoing thin film technology, which was invented in the early 80s, has resulted in the ability to produce reliable platinum RTDs at such low cost that wire-wound platinums are now only used in very specialized applications. The standard 100 ohm degrees at 0C was accepted quickly, and wire-wound platinum elements were now used only for specialized applications, mainly for things like laboratory use, where they can be made to be more accurate than a thin film sensor, but they're also much more fragile in those configurations. There are other popular resistance levels out there other than the 100. There's 200, 500, 1,000, and 2,000 ohm units. But when you start getting up into the high end here, you have heating issues, self-heating issues, so you've got to compensate for that. Two types of RTDs, wire wound and thin film, are still being used widely, although thin film is taking over in the industry. It's much more rugged. You have a sensor that you're running an electrical voltage through and getting a differential back to a readout device. Wire wounds can be made in three basic configurations. Unsupported wire or bird cage, which is very fragile, but is used in what's called SPRT, specialized RTDs for calibration use. Partially wire supported and totally supported construction like this, where all the wires are supported by a ceramic or glass covering. The first is extremely fragile, the second relatively fragile, and the third very rugged. However, the more supported the sensor, the better matched the expansion coefficients of all the components need to be to prevent strains, which affect accuracy. The technology of sputtering thin film platinum devices resulted in the addition of controlled amounts of impurities and or stabilization exposures. They sputter molten platinum onto usually a little ceramic chip, and then they laser cut it to trim it to get the proper resistance levels. And these are good up to about 8 to 900 C and are used throughout industry because they're much more rugged and vibration proof than wire wound RTDs. And these are built to either the DIN 43760 standard or the IEC 751, which are pretty much comparable. Here are some wire wound glass coated RTDs. They're coated to protect them from things they might be exposed to, and also to keep them stable because the glass is poured around them. Thin film chip, these are built in various configurations. This one's rather long, some of them are much shorter, not being much larger than this blue part here. The thin films are made to what's called a Heraeus method, where they're built in large volumes and computer laser trimmed. Then there's tested for accuracy. The ones that meet the Class B accuracy are sorted out, or Class A are sorted out as Class A's. The ones who fail Class A are checked for Class B. If they meet those standards, they're sorted out. If they do not meet that, then they go to Class C, and so on. And we'll get into what those mean in just a moment, the Class A, Class B, and Class C. Resistance type sensors offer a number of advantages: more accuracy and stability, several levels of performance. We're talking about Class A, B, and C. High accuracy, easily obtainable, best long-term stability, great resolution, relatively fast temperature response, again, a function of the mass of the sensor. Very highly repeatable. For long term, they're by far the best sensor. The most linear of all common available sensors. Precision versions do not require microprocessor for linearization. Relatively wide ranges available, better than most thermistors. Disadvantages: requires a power source versus a thermocouple. A relatively fast response, but much slower than a thermocouple because of the mass. Relatively wide temperature ranges available, but much less than a thermocouple. They're most likely to be damaged by excess mechanical shock, much more than a thermistor or a thermocouple. More expensive than other sensors. Some configurations are difficult to mount. They require a larger diameter probe to insert a sensor in, because you can't make them as small as you can a thermocouple. Some self-heating issues in the higher, especially the higher resistance levels, and lead wire resistance issues is a big problem. So the RTD element has copper lead wires, positive and negative, attached to opposite ends of the element, and these are powered by the meter or an external device. This RTD element has a known resistance level at a given temperature, so we're looking for a change across that element from one side of the element to the other. The copper wire leading from the probe up through a handle or cable assembly on a handheld probe or being transmitted will add significantly to the error if you run along lead wires. On a 2-wire, you can go up to about 5 feet in length for most applications with no significant error unless you're trying to have a precision reading. For long lead wires, you need to go to either 3 or 4 wire. The extra wires allow the lead wire resistance to be calculated out of the total so that we get the true resistance from one side of the sensor to the other. 4 wire is better, allowing the actual measurement of both legs of the circuit. The 3-wire measures one leg and calculates the other, assuming it's the same. It's not always true, but it's the most commonly used in industry because it accomplishes most of what a 4-wire does with less expense. So here we have the sensors, 2, 3, and 4 wire. So what we're doing is we're running a current through here and goes through the sensor and goes out, and this goes back to your meter. The current also goes down this leg and this leg to the meter, and connected between these two is an ohm meter. I don't care anything about this. All I care about is the difference from here to here. So this ohm meter is reading these two, and that's giving me my temperature reading. And this is your power circuit. On the 3-wire, we're assuming this missing wire will be the same as this, and that's not always true. Not a lot of difference, but there might be a small error depending on the accuracy you're requiring. So the PT100 sensor is basically a resistor. Its value is measured by an ohm meter. The 385 DIN curve or IEC 751 curve is the most common. There are other sensors that have similar curves. There are 2 American curves that are 392 with a 4th decimal point. That's 2 different ones, which is used in some places, but the 385 is the most common. A 1 ohm resistance in each lead wire. These lead wires connecting, if you don't have these extra wires taking it out, can cause an error of more than 5 degrees C. So the best way is to use the 4-wire, and you want a voltmeter that's high in impedance so that there's a few ohms in resistance. The cables will not cause an error. So we talked about the compromise between the 3 and 4-wire. This is the most commonly used in industry. You're calculating that the missing wire is the same as this one. So this wire and this wire here are doing this and this combined with the power source on this side. So these are some tolerances for RTDs. Class A, you will see, has a resistance level that is here at 0C, which is the platinum, 100 ohm platinum, is allowed a 0.06% resistance error at 0C. What that means is an RTD, 100 ohm RTD, can be 99.94 to 100.06 and still be a Class A. When you buy a probe from us, you will get a tag on it that gives the R0. And what that's doing is to say it's 100.03, it's telling you to take that small error out of your meter when you connect it up. And so you've zeroed out that tiny starting error. You will see a Class B has twice the allowed error as a Class A. So keep that in mind when selecting your sensors. So the advantages and disadvantages: thermocouples operate over a wider range. RTDs will go lower than a thermocouple on the bottom end, but they won't go as high on the top end. Thermistors are generally low or short range span, but the accuracy can be very good. RTDs are best. Linearity, you can see the differences. Thermal response, RTDs are slow compared to the other two. Cost, RTDs are higher compared to the other two. Noise problems, you should be shielding your RTDs also. This is very low voltage here. This is medium voltage. This is a high resistance voltage, so you don't have much of a problem with noise issues there. Long-term stability, RTDs much higher than either thermocouples or thermistors. The cost is highest for RTDs and the meters, but if you need accuracy, that's the best way to go. On a thermocouple, you have to add the accuracy of the meter and probe together. Most of the time, RTDs and thermistors are sold as a system where the two readings are combined together. When you're checking off different types, you choose a type of thermocouple. The types here are the two different alloys and the two wires that are put together. The RTDs, you choose a 2, 3, or 4 wire, grounded and ungrounded exposed tips. For thermocouples, all RTDs and thermistors are ungrounded. Sheath construction, the material of the probe that you want based on what it's exposed to. Very high temperatures or corrosive materials require more exotic metals. The diameter and length, whether you want a hollow tube with just wires coming through or you want a magnesium oxide filled. Type of connection to build the probe up. Compression fittings, ring terminals, pads to be welded on, NPT or bushings. Lead wire length, type of wire, the gauge, and whether you want solid or stranded wire. A stranded wire will carry more voltage and have less resistance than solid wire will at the same gauge size. Wire insulation, the type of insulation, what's it exposed to. If it's a high temperature exposure, you're going to need a different insulation than if it's low temperature. Mechanical protection, you need a braid covering or armor on it, and the type of connections on the end of your wires you're going to hook up to. So if you want to determine some ways to determine which sheaths, which probes to select, what are the temperature requirements? If it's say minus 200 to 500 C, an industrial RTD is the best way to go for accuracy. If you're going above say 800 C or 850 C, you're going to have to go to a thermocouple because RTDs will not operate up there. Speed of response, if that's an issue, fastest is thermocouples. But if your accuracy is your issue and you need speed of response and accuracy, maybe a thermistor if it's a low temperature. So there are different ways of measuring these things. These are some of the ways we measure them. Size requirements, RTD sheath is 3.17 to 6.35 millimeters, up to a 1/4 inch, 1/8 inch diameter. That's about the smallest we can do with an RTD. You can't get a chip any smaller that will go down in it. With thermocouples, you can get thermocouple wire as fine as a human hair, so you can get very small diameter probes. Accuracy and stability requirements. If the tolerance is 2 degrees C, it's acceptable, and the highest level of repeatability is not required. a thermocouple will serve. RTDs are capable of higher accuracy and can maintain stability for many years, while thermocouples will drift fairly quickly depending on how many cycles they're going through and the temperatures they're exposed to. If you have any questions, we'll be glad to try to answer them here, or you can send an email. If you have any future questions you can think of, I'll be glad to answer them. Send me an email and I'll get back to you as soon as I can.